You're already aware that there's a gold mine of information tucked away in Section 5 of your Skyhawk's POH. Now you'll discover how to dig more nuggets out of that mine. Wind, as you know, can affect your Skyhawk's takeoff performance, especially if it's not aligned with the runway. When you evaluate its effect on performance, it can be helpful to think of it as two separate winds called components. There's the headwind or tailwind component, which has the same effect on performance as a wind blowing directly along the runway centerline. The other is the crosswind component, which acts on your Skyhawk the same as a wind that's running perpendicular to the runway. Let's suppose that ATIS reports runway 2 is in use. You'd know right off that your path of flight for takeoff or landing on that runway would be 020 degrees. Of course, all you had to do to know this was to add a 0 to the runway number. Now let's assume that the same ATIS told you the wind was from 340 degrees at 23 knots. The first thing you'd want to know is how many degrees off the runway the wind is. Normally, all you have to do to find this out is subtract, but in this case, the wind is one side of north and the runway is the other side of north. So what you can do is find out how many degrees each direction is from north and add them together. The wind is from 340 degrees, so how many degrees from north is that? Well, north is 360 degrees, so 340 degrees is 20 degrees from north. The runway is 20 degrees from north. So add them together and you find out that the wind is 40 degrees off the runway direction. Now let's take a look at the wind component chart. Your Skyhawk POH, PIM, and the slide of your flight computer all have this handy graph that's used to determine wind components. And they're all there. There's the crosswind component, the headwind component, and the tailwind component. You'll also notice these lines radiating out from the 0 wind point. These lines are for wind direction off the runway. If the wind were more than 90 degrees from the nose, you get the tailwind component. Less than 90 degrees, you get the headwind component. We'll use the headwind or tailwind component later on when we do takeoff and landing charts. Back to our example. We have a 40-degree wind direction off the runway. Now, this line is for 40 degrees. Also, notice the wind strength arcs. There's one for 5 knots, 10 knots, 15 knots, and so on. We have a wind strength of 23 knots, which is going to fall between two of the arcs, between 20 and 25. So make a dot right here at 23 knots, right between the 20 and 25. Now you're going to read horizontally across to your left from that dot, and you're going to find the headwind component. In this case, we get a headwind component of about 18 knots. In other words, this wind is equivalent to an 18-knot headwind right down the runway. Now read straight down from the dot to get the crosswind component. In this case, we get a crosswind component of about 15 knots. In other words, this wind is equivalent to a wind 90 degrees off the runway direction at 15 knots. Pretty easy. But it doesn't tell you whether the crosswind is from the left or the right, but you can see that, right? And the team back at the factory has demonstrated that your Skyhawk can make takeoffs and landings with a crosswind component of 15 knots. That's really a lot. Now, it may be able to handle even greater crosswind components, but so far nobody has tried it, and you probably don't want to be the first. Now let's take a look at the time, fuel, and distance to climb chart. You'll use this chart to figure out how much time, fuel, and distance will be used on your climb. Now up here you see that the data are for flaps up, full throttle, and standard temperature. So what is standard temperature? At sea level, it's 59 degrees Fahrenheit or 15 degrees Celsius. To keep it simple though, standard temperatures are listed with the corresponding altitudes in this column. Notice that at the sea level standard of 15 degrees Celsius, they drop exactly 2 degrees Celsius for each 1,000-foot increase in altitude. Remember where this column is. You're going to find that this too will be handy in the next lesson. Now let's say you're departing an airport where the pressure altitude is 2,500 feet and the temperature is 25 degrees Celsius. Let's further suppose you'll climb to a cruise altitude of 7,500 feet. Well, here's something a bit different. You start with the takeoff elevation, then find the difference between those values and the cruise values. You can see the reasoning here, of course. You were already at 2,500 feet when you took off. To keep it simple, don't interpolate. Go to the next nearest value that offers a conservative result. That's one that has you overestimate the time, distance, and fuel used to climb. In this case, use 2,000 feet and 8,000 feet. So following those values across, you would get time by subtracting 3 from 15. That leaves you 12 minutes. To get the fuel used, you subtract 0.7 from 3, and you get 2.3 gallons. And to get the nautical miles, you subtract 4 from 21, or 17 nautical miles. Looking down at the bottom of the chart, notice that Note 3 says that you increase time, fuel, and distance by 10% for each 10 degrees Celsius above standard temperature. That's the hard way of saying increase the values 1% for every degree above standard. Your takeoff temperature was 25 degrees Celsius at 2,500 feet. Looking at the standard temperature column, you see that halfway between 2,000 and 3,000, the standard temperature must be 10 degrees. So 25 degrees minus 10 degrees tells you that you are 15 degrees warmer than standard. For convenience, you assume that the temperature difference is constant up to cruise altitude. Well, 15 degrees warmer than standard adds a 15% penalty increase for all values. Let's show you what that means. A 15% increase applied to 12 minutes, rounded up, is 14. Let's skip fuel for the moment and do the mileage. 15% added to 17 nautical miles, rounded up, is 20. While helpful as a rough estimate, the mileage figure doesn't account for wind. It also doesn't account for the traffic pattern conditions, which might send you in the opposite direction for several minutes before you can turn on course. Now, back to fuel. 15% added to 2.3 gallons, rounded up, is 2.7 gallons. That isn't a very big correction. Some line boys spill more than that, just taking the nozzle out of your tank. Now let's look down here at Note 1. You're going to add 1.1 gallons of fuel for engine start, taxi, and takeoff allowance. So you're going to add that 1.1 to 2.7 gallons you just calculated for a total of 3.8 gallons. This allowance should bring you comfortably from the parking ramp up to cruise altitude. Notice, too, that you rounded up at every step and took the most conservative interval to begin with. Congratulations, you've just mastered one of the more complicated charts in the section. So why don't you rest on your laurels, or whatever you like to rest on, for about, the next 10 seconds, and then take the practice questions.